This is lecture 11 of an introductory class in electricity and magnetism. And in this lecture, it's going to be a little bit of, it's not really a summary, it's more of, let's think about what we've got. See some more examples of the various things that have been going on in the first 10 lectures, but seeing them sort of close to each other, and maybe getting some thematic commonalities amongst all the topics. So it's got one, I'm calling it an ish learning outcome. It's not necessarily a learning outcome because you're just getting some perspective on how to use various techniques. Yeah, and so we're going to start with Gauss's law, where for the Shell Theorem. So the Shell Theorem is something I introduced quite a lot of lectures ago. It was when we talked about electric force, so maybe lecture number 3 or maybe lecture number 4. But the Shell Theorem was about a spherically symmetric charge distribution on a shell. And so maybe Gauss's law can be used to get the Shell Theorem. So I'm going to remind you of what the Shell Theorem is, and then extend it to thinking about the electric field, because the Shell Theorem is, as far as we've talked about it, is about force. And then Gauss's law, of course, is about electric field and not necessarily about electric force directly. So the next topic after that, I'm going to describe, in this case, a ring of charge, which we've also discussed determining the electric field for it. And of course, this ring of charge is a sort of uniformly charged ring or circle. And so there's quite a lot of symmetry in this charge distribution. So I'm going to show you what it looks like to try to use Gauss's law to get the electric field of a ring of charge, and show you that it doesn't have enough symmetry in order to get fully the electric field. And then another example, or sort of like collection of thoughts, is the fact that we can sort of build what we need sometimes. And what I mean by that is we've got a lot of results. We've got a Shell Theorem result. We can use Gauss's law. We've got we've done some stuff about determining the electric field of a charged rod, etc. So I'm going to show you an example of using lots of these results in order to solve a simple problem, where if you just took the simple problem and tried to solve it all from a very basic first principles starting point, it'd just take forever. So you want to just use what you've already built and build what you need from it, is kind of the idea. So I'll show you an example of that. And then also I'm going to show you that you still need to be careful when a material is being described as a conductor. So I'll show you an example where at first the solution looks really, really easy, but then conductors, they do something with their charge, and so we have to be careful. Okay, yes. So let's start with the Shell Theorem. So the Shell Theorem is actually, we introduced it early on in an earlier video. It's actually about force, as far as that early video is concerned. And the Shell Theorem is sort of 2 statements. It says that if a little charge, or not necessarily a little charge, but if there is a charge, lowercase q, located outside of a uniformly distributed charge over a spherical shell, so little q is outside of the shell. So let's say that the distance to little q is called little r, right? And this is the distance actually from the center of the shell to the charge q. then the force on little q is equal to q times little q divided by 4 pi epsilon naught little r squared if little r is bigger than capital R. But it also says, the Shell theorem also says that if the charge lowercase q is located inside of the shell, that is lowercase r, which is the distance from the center of the shell to the charge q, is smaller than the distance from the center out to the outer edge, that is the little charge q is on the inside of the shell, then what's really interesting is the force on little q is just 0. It's like all of the charge on the right hand side of the shell, all of this charge, right, which is on a little dome, is let's say capital Q and lowercase q are just both positive types of charge, so they're repulsive. So they're repulsive in this case. In this case, this little dome will push to the left on lowercase q, and this little dome, or the rest of the dome, will actually push towards the right of precisely the same amount of force, so that the net force on lowercase q by all of the charge distributed around the sphere just adds up to 0. The fact that it adds up to 0 is the special thing. It's got to do actually with Coulomb's law, the fact that Coulomb's law is a 1 over distance squared law. It's an inverse square law. Okay, so if we extend Shell theorem to electric field, we would say this. When we ask about a place that is outside of this uniformly charged spherical shell, the electric field at this location right here has a magnitude equal to, so the charge capital Q is smeared uniformly over this shell of radius capital R. The electric field has a magnitude that's 1 over 4 pi epsilon naught, and then just 1 over r squared. And actually, we need to know the charge capital Q. So that is when r is bigger than the shell's size, radius. And then we would also say that if you go inside of the shell at any radius r that's smaller than the radius of the charge distribution, then for lowercase r values that are smaller than the size of the shell, the electric field simply has value 0 everywhere in there. Over here, the direction is, it's sort of the same way that we think about repulsion or attraction over here. So the direction is outwards from center if little r is bigger than r, right? So this is also known as radially out, but only if the charge capital Q is positive, and if the charge capital Q is negative. So if charge is positive, it's outwards from the center, right? Radially out. And this is instead radially in. So this would help us build the field line diagram. And then regardless of the sign of the charge, there is no direction in this case because we don't have a magnitude. We just have electric field equal to 0 everywhere on the inside, and the electric field everywhere outside is not 0. And so we would say that the field line diagram might look like something like this. So the field line diagram is just the field line diagram of a positive charge outside the shell and inside the shell. Maybe we would say something like that. So on the inside the electric field 0, and on the outside the electric field is identical to the electric field of a point charge located at the center. Alright, so that's an extension of the Shell theorem to talking about electric field. But I wanted to do something like this. I'm going to show you how you can get the Shell theorem from Gauss's law. So Gauss's law says that over an arbitrary surface S, if you calculate the flux of the net electric field of a charge distribution, then all you will ever get is the charge enclosed by my arbitrarily chosen surface S divided by epsilon naught. That's the guarantee associated with Gauss's law. So let's say that this is the charge distribution. So Q is uniformly smeared over the surface, over a shell of radius capital R. So here it is. This is our charge Q, and it's got a radius capital R, like this. Alright, so here's our charge distribution. So the symmetry of the charge distribution suggests spheres as Gaussian surfaces. What's more is the symmetry is limited to this center. So the center of the charge distribution, there's only one center in a sense. I know that's funny to say. But these Gaussian surfaces, they are spheres, right? Spheres is Gaussian surfaces. And these surfaces must be concentric with the charge distribution. And concentric just means that they're going to all share the same center. So let's study the case of, here is the charge distribution, and we're going to ask, well, what if we study a Gaussian surface whose radius is bigger than R in one case, and in the other case, you can probably guess what I'm about to draw. Let's study Gaussian surfaces with radius smaller than R, right? So this will be like case 1, and this will be case 2. So let's look at case 1 first. So case 1 was the case of our little spherical distribution of charge being completely enclosed by the surface S. And the surface S is a sphere centered concentrically with the charge distribution Q. So in this case, Q enclosed by S is all of the charge of our sphere. So that's what case 1 looks like. So when we do Gauss's law and we ask what is the flux of electric field out of this surface, we already know that it's going to equal Q over epsilon naught, where that's the charge of the spherical shell that's all enclosed. So what happens then is a couple of things. We ask, what about the relative direction of E and dA over S? Right, so over this surface S, we have no reason to expect that, right? If I draw the field line diagram, the field line diagram has to have this spherical symmetry. So here I'm drawing a field line diagram with spherical symmetry, and the area elements of S are just little vectors that point outwards from the surface everywhere. So if you look outwards from the surface area, over the Gaussian surface, E and dA, if we check so let's check relative direction between E and A over S. Everywhere on S has the situation that E is parallel to dA. So E dot dA is the same thing as the magnitude of E times the magnitude of dA. So now Gauss's law becomes Q over epsilon naught equals the integral over S of the product of the magnitudes rather than the dot product. What's more, because of the spherical symmetry, the magnitude of E only varies with R. And what this means, it implies that E has, so what does this imply? It implies that E has the same magnitude everywhere over S, because S is a constant radius surface. And so that means that the integral of E over dA over the surface, so if I stay on the surface, which is what this integration does, so I stay on the surface and the value of the magnitude of the electric field is always the same no matter where I'm at on the surface, which means that the magnitude of the electric field is a constant of the summation, and I'm left over with this. And the area that I'm adding up is the area of that sphere, that Gaussian surface, which is a sphere of radius lowercase r. So I can actually tell you what the result of integrating up the area is, right? So this thing is the area of S, and S is a sphere of radius lowercase r, so it's 4 pi r squared. And so with Gauss's law, we can go right up to the top and say the flux integral over this surface S we had reason to say that it had to be just the product of magnitudes. The magnitude of one of the factors inside of the integral is actually a constant over the integral, so it came out. So this is the flux over the surface S. So this right here is, we've determined by Gauss's law, it's just the charge enclosed in the surface, which is capital Q. It's all of the spherical shell of charge divided by epsilon naught. And this gives rise to saying that the electric field has a magnitude equal to Q over 4 pi epsilon naught r squared, like this. The direction, we've already determined it, because the direction we know from earlier symmetry argument. So it's actually really quick, so I'm going to do it here. Case 2, same symmetry, right? So even in case 2, I have all of the same symmetry for the charge distribution, which means that when I calculate the flux, all I'm going to get is the same stuff. It's going to go all the way down to the integral of the area over the surface S. And the surface is still a sphere, or the surface of a sphere, so it's 4 pi r squared. But the thing is if you look at case 2 has the charge distribution Q, and we have a Gaussian surface on the inside. So the Gaussian surface encloses no charge. So if it encloses no charge, then by Gauss's law, which is the flux is Q enclosed over epsilon naught, Q enclosed is 0. So when I divide by epsilon naught, I still get 0. And what this says is that the magnitude of the electric field for R values inside of the surface, you just get 0. And this is the Shell theorem. So instead of doing a crazy integral where we split the surface up into charge elements and then add up the net electric field due to all of the individual little bits of charge, we instead invoked a symmetry argument and Gauss's law to actually just say that, well, outside it behaves like a point charge, and inside it behaves as if there is no charge anywhere. So that's interesting. So that's the Shell theorem. The next example is to think about a charge distribution that has some symmetry, but it's not enough symmetry to fully exploit Gauss's law to get the electric field. And the charge distribution that I am going to use to exemplify this situation, although it is definitely not the only one, there are many, many kind of symmetric charge distributions, but that simply don't have enough of the special sort of amount of symmetry required. This case is the ring of charge, not a disk. So I hope that you by now... So I'm treating the ring of charge in this example, but not the disk, although actually the disk has exactly the same set of issues, turns out. But I'm doing the ring of charge, and I hope that you know by now that the ring of charge is different from the disk of charge. Yes, so I'll just point that out. But yeah, we're talking about the ring of charge. So I have a uniform ring of charge, uniformly charged ring of charge, and the charge density is this linear charge density lambda, and the radius of this ring is capital R, and so the charge of the ring is the circumference, 2 pi r, times the charge per unit length, lambda. So 2 pi r lambda is the charge of the ring. So
from before, this is a result of using the Coulomb's law version of calculating the electric field. What we had to do was we imagined splitting this charged ring up into little charge elements, and then going to somewhere and asking what is the electric field from each of the charge elements, and then calculating using the superposition principle the net electric field there by integrating up the contributions of electric field from all of the point charges around the ring. And we only did this, I don't know if you noticed this, but we only did this on the axis of symmetry. So what we determined was that we could write down the strength of the electric field based on how far away from the center we were, but we were only allowed to describe the electric field in a perpendicular direction away from the plane in which the ring of charge exists. So, for example, if these are the say x and y axes, and then the up-down axis is left over to be the z, then we only ever determined the magnitude of the electric field along places on the z-axis. We did not go off the z-axis, so we've only done the problem for on the axis of symmetry. If you wanted to do it off the axis, you'd have to think a little bit more, and you'd end up with a slightly tougher integral. But here's an example of a place off the axis. So let's say that this position here, it's not on the z-axis, it's over in x and y, and what's the electric field? So the electric field over here is going to be probably some arrow like, say, this, right? Because all of the charge on, say, this side of the ring is going to push this way on a test charge, and all of the charge on this remaining side of the ring is going to sort of somewhat push upwards. And so that way and upwards is this arrow over here. And if I check further away, I would determine likely that the electric field is quite a bit smaller in strength because I am further away from the charge, and maybe there is somewhat different direction, right? And if I checked over here, I'd expect that the electric field pointed just away from the ring, and over here, if I was sort of symmetrically the same distance away, then I would just get the same amount of force per test charge, but it would be in the opposite direction, right? And then up on this side, if I was the same distance away as I was there, right? So I've got some symmetry, but it turns out it's not enough, and I'm going to sort of describe the issue of it not being enough. So here's the thing. If you actually sit and try to think about what is the field line diagram's sort of shape, you're going to get a picture that looks like this. And this is sort of tough to draw, but let's imagine that for the purposes of our arguments, that the charge is positive. What the field line diagram is going to look like is it's going to have sort of a cylinder symmetry, which is suggesting using cylinder shapes possibly for Gaussian surfaces. But it's not really cylinders that we want. Let me show you what I mean. So if I was going to draw the field line diagram, it points away in the plane of the ring. So in the plane of the ring, it points away. But if I go off the plane of the ring above, what I'll discover is I've got to divert the field lines like this. So, for example, this one is going to end up coming out of the page this way, and this one back here, it's pretty tough to draw this, but the idea is it goes into the page instead and behind. Yeah, and I've got sort of similar ones coming out of the page up to the right, but at the same time I've got the ones that are sort of like related to those that point down the page. It's starting to maybe not be easy to see what I'm trying to draw. But the point is like the field lines kind of like come away from the ring and then outwards on above, but they also do that below the ring, right? That's how the field line's got to look. And very, very far away from the ring, if I go very far from the ring, it just looks like I have a point charge Q, and I've got field lines that are just like a point charge, right? So they're coming out in these directions, but also there's a field line sort of coming out, and it just looks like a spiky sphere or something like that far away. The field line associated with the z-axis is sort of hard to draw because I don't have an easy way to depict in this close-up shot a point charge for the field to come away from along the z-axis. But I hope you can see that even though a field line is not in a location like along the z-axis in this drawing, there is an implied strength of field there based on the density of the nearby field lines. Anyways, so I definitely have some symmetry, and the symmetry is cylindrical. It's cylindrical in the sense that if I took this ring of charge and imagined rotating it, there is no real physical change to how the field lines look. But if I so that's what's meant by a cylinder symmetry, is if I was able to grab onto the ring and rotate the ring around, then I would not be able, like no test charge that is sitting out here would notice any difference. The test charge would just simply, the force on the test charge would not change. So that means that the electric field is not changing. So that's a symmetry of the electric field. So I'm going to try to draw this from a side perspective and I don't know, clear up the picture a bit. So from the side, there's the edge of the ring of charge, and the field lines, they're going to look like something like this. So that's what they look like on the right side, and on the left side is just symmetrically the same stuff. It's like a mirror image. Let me see, I think it must be like this. Yeah. And you can see what I mean by the z-axis. It's tough to imagine a field line for the z-axis. But the field line for the z-axis is sort of related to the density of the nearby field lines that I'm drawing. Okay, so this is the field line diagram. And so do you remember that the steps for thinking about how I can simplify this flux integral? So here's the flux integral. And the pattern of simplification is, first of all, we realize that S can be split up into parts where S is parallel and S is perpendicular in a sense. And what I mean by this is when E dot dA is integrated over the parts of the surface where we have parallelism, what I'm referring to is these are the parts of the surface where the electric field is parallel to dA. So this is the integral over the parallel parts of S of just E times dA, right? And then also, though, is that there is an integral over the perpendicular parts of S, and what that means is that this is equal to 0. So this happened in the case of the infinitely long, straight line charge, uniform line charge density. It did not happen. This did not happen in the Shell theorem example I just did. In the Shell theorem example, we only had all of S was a parallel situation between electric field vectors and the area elements that define S. That was the Shell theorem example, had that. So if we can find a surface such that the surface is only ever either parallel or perpendicular, then we get to have this really interesting simplification that this can become EDA magnitudes over only the parallel part of the surface. So let's try to force that to happen. What I'm going to try to do is force it so that the surface is always perpendicular to the field line. And the truth is that's actually quite easy to do, although the definition of that surface mathematically is, I'm not sure what that surface is. I don't know if it's like ellipses necessarily, but it'd be interesting to actually figure out what this surface needs to be. But here, I'm going to draw it. So perpendicular, 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 and perpendicular, and I'll just connect the dots. And this is a surface. It's not very well drawn, but I think you understand what I'm saying. This surface is such that E is parallel to dA everywhere. So that's good, which means that I have been able to do this. So this is good for this surface. The problem is the next step is not going to happen for us. Problem is, over this surface S, the magnitude of E is not constant. So that's quite interesting. The magnitude of E over a surface like this is a complicated function of the coordinates associated with places along the surface. So the next step that we depend on, that the electric field has a constant magnitude over the surface, this is the step that can't happen. So the idea is we don't have enough symmetry to have both of these steps happen. And so what this means is we cannot get E from exploiting Gauss's law because it's not enough symmetry. There is some symmetry, but it's not enough. So let's continue with building, in quotes. You can figure out what that means for yourself, what we need. So let me tell you, here is a charge distribution. It's somewhat complicated, but it's not that complicated. So on the left here, you've got a uniformly charged shell whose charge is Q1, uniformly spread over the shell, spherical shell, with a radius R1. So you can imagine these have some values. Here's a point charge Q2 and another point charge Q3. So if we think about, let's think about electric field first. Um, there is an electric field due to the sphere of charge. There's an electric field due to the point charge Q2, and there's an electric field due to the point charge Q3. Um, and these three things you could superpose. And what you would get is the net electric field because of all three charges. But what if I wanted to know the following thing? What is the force on Q2, for example? Right, if I wanted to know the force on Q2, I will not use the net electric field, which includes the electric field of Q2. I hope you can see that. Yeah, in fact, if you did use the electric field of Q2 as a force on Q2, you would get infinity as the answer. Because the idea is Q2 is infinitely closer. It's right on top of the source for that field, and so you would be using a 1 over r squared, right, inverse square law for Q2, where r is equal to 0. And you'd find an infinite contribution to the force on Q2 by its own field. So what you'd have to do is you'd have to figure out that Q2 feels electric field due to Q1 and Q3, right? So if you wanted to know what electric field Q2 feels, it feels the electric field by the other charges in the world, not its own electric field. Okay, so in order to figure out the force, actually, it's pretty easy if you know how far away Q2 is from the center of Q1. You just use the Shell Theorem, and then you'd add to that the vector force on Q2 by Q3, right? So if you want to figure out what is the force on Q2, it's equal to the force on Q2 by Q1, and you'd use the Shell Theorem, and you'd add on to that what is the force on Q2 by Q3, and this is a simple exercise in Coulomb's law, and then you'd superpose the forces, the vector forces, to get the net force on Q2. How about this? Here's a new problem. So here is Q1 with radius R1, so it's the same thing, and here is Q2. And we know that the force on Q2 by Q1, the way you get this is with the Shell Theorem. What you do is you would say that this sphere can be treated as a point charge. But what if we wanted to know what is the force acting on the shell, right, the totality of the shell, by the point charge Q2? Can you see that these are backwards questions? This one here is associated with Q2 being pushed to the side by Q1. So here's Q1 pushing on Q2. So this force is this arrow. But this force right here is the force acting on this assemblage of distributed charge by Q2. And the answer here is given by Newton's third law, right? For every action, there is an equal but opposite reaction. And so if this is the action, then this thing is going to have a reaction force the same size but opposite in direction, right? So you can get it from Newton's third law. And that's a kind of an idea about building what we need. We just have to think about some physics, and then we can sort of build what we need. If I wanted to add up this net force, right, in a different way, what I have to do is consider the interaction between this point charge and every charge on the surface of the shell. And I'd say that every one of these little charges was feeling really tiny little repulsion forces. On the top side, it's kind of upwards like that because the repulsion is in that direction. And then on the bottom side, the little point charges dq are feeling forces instead like this, right? Because that's what the repulsion looks like for the lower charges. But the downness and the upness, because of the uniformity, the down and the up are going to add up to 0. But all of the sidewaysness is all towards the left. So you just add all of the leftwardnesses together, and all of the leftwardnesses would just add up to be the same side as that, same size as this arrow, but leftward instead. So that's how Newton's third law would work. Yeah, it's the Shell theorem again. But let's update this to ask an interesting question. What if I had two shells of charge? So here is a shell of net charge Q1 uniformly distributed over a spherical surface of radius R1, and here is another one. And this one is a charge Q2 spread over a spherical surface of radius R2, and it's done uniformly. Okay, so here's what's interesting about this situation. The magnitude of the force acting on Q1 by all of the charge Q2 is equal to the magnitude of the force, acting on Q2, so the reaction, by Q1, so that's magnitude. And these are both equal to, and this is pretty cool, 1 over 4 pi epsilon 0, Q1 times Q2 over the distance between them squared, which I didn't give a symbol for. So let's say that the distance between them, d squared. But this is true only if d is bigger than R1 plus R2. That is, what this means is it implies that there is no overlap of the shells of charge. What about an alternate case? What if I took the shell of charge that's bigger and put the shell of charge that's smaller inside of it? So this is the center of Q2, and this is the center of Q1, right? So in this case, every charge of Q1, that is every charge dQ, right, every small piece of charge associated with the Q1 sphere is inside of Q2's shell. So the Shell theorem says that the force on any charge element of the sphere Q1 by the sphere of charge Q2 is always equal to 0. And what's interesting is this is actually a vector, and it is an infinitesimally sized force, right? This is the net, that's the small force on the small charge element, for example. This could be the charge element we're talking about, so this could be dq1. The Shell theorem says that all of the pieces of charge that are inside of a uniformly charged spherical shell, all of the ones that are inside feel a force 0, which means that if all of the charges, if all of the elements of charge are on the inside, then the net force is going to be 0, right? So that means that the force on Q1 by Q2 is going to add up to 0, just because of using the Shell theorem. And this also implies, by Newton's third law, that there is no force on the outer shell of charge by the inner shell of charge, right? This one is Newton's third law. Okay, so that's a use of the Shell theorem. So let me tell you what we can't say is true. What if we had Q1 with radius R1 overlap with Q2 of radius R2, right? In this case, sum of Q1 is inside of Q2, but not all of it. So what this means is that so this is not so simple. You can partially use the Shell theorem to solve this problem. So I'm suggesting a partial use of the Shell theorem to solve this problem, but the integration will be non-trivial. The idea is if I was going to maybe start setting the problem up based on this decision here, I would take all of this and ignore it because it's on the inside of Q2, and this is the leftover. And so what I'd have to do is use the Shell theorem on charge elements over the rest of the surface. Right, so these are small elements of charge over the surface of the shell of charge number 1. Yeah, so you'd have to figure that out. Maybe it would look kind of like this. So you'd say that here is Q2 and glommed onto it in a sense. So let me is just Q. This is the part of Q1 that you would keep. This is the leftover part. Yeah, so that problem would be a little bit more difficult. Okay, so those are suggestions on how to think with some of these ideas about forces and electric fields using the Shell theorem, using Gauss's law. So one last caution when you have conductors. So let me show you something. So let's imagine a conductor with charge Q sub c. So this is Q of the conductor, is a sphere of radius r sub c. And so if you look at this conductor with this charge on it, conductors are special because if a conductor has a net charge, this net charge lives only on the surface. And part of the reason for this is what I showed you before, is that the fact is that the electric field in the bulk of a conductor can only ever be zero. And the way you do that is to, in the case of a sphere especially, is to distribute the net charge only over the surface in a way such that the electric field of that net charge is zero on the inside. So in the case of a sphere, this charge would be a uniform spherical shell of charge. Right, that's what a conductor would do. So then, now I've got a uniform spherical charge, shell of charge, because that's how conductors will deal with their own net charge. So this net charge is spread over the conductor. Okay, so now the thing is, though, is what if I asked, what is the force between this charged conductor and, say, I bring in from really far away a charge little q. So here's little q, I bring it in. And let's say that q is positive and the conductor charge was positive as well. So the reason why you have to be cautious is because this charge, if this is a conductor, this charge is going to alter the charge distribution here, because this charge has an electric field that will be inside of the conductor until the conductor moves charge around to get rid of the electric field, because the electric field in a conductor cannot be anything but zero for a long time. And so what's going to happen is this, because of the presence of this, is no longer uniform. In fact, it polarizes partially. So instead, this spherical conductor is going to be something more like the following. It's going to be slightly less positive on the nearby side and more positive, or a higher density of positive, so I'm trying to draw them all closer to each other, on that side. So this is no longer uniform, and I cannot use the Shell theorem. So when you see a conducting material having that charge, you have to think a little bit, but you should try to decide whether or not your charge distribution is going to stay uniform. If a problem starts off by saying a non-conductor with charge q sub c has a uniform charge density, then even when you bring in or imagine other charges nearby, a non-conductor is the type of material such that in homework problems you should assume that the charge density cannot change. So that's the caution.